All right, it's time for a discussion of some new topics from Chapter 3. We need to talk about the ionic bonding and from our learning objectives and the formation of binary ionic compounds from their elements, in other words, two kinds of elements. And we're going to talk about lattice energies a little bit, deciding about how that works, and a little short discussion about what the Born-Haber calculation entails, not that you'll ever have to do one. And we'll talk about those other topics subsequently. This section of the chapter starts out with a rather interesting looking chart that may overwhelm and befuddle you to begin with. So let's see if we can sort it out. The formation of an ionic solid, such as sodium chloride, is summarized with the net reaction that's shown on the left. The net reaction is this. A sodium atom combines with half of a chlorine molecule, in a hypothetical sense, to make sodium chloride as a solid. The value of the energy change for the formation of that solid has an energy of that number of kilojoules per mole. Where in the world does that come from? It has to do with where all the individual steps are that factor into this reaction, and let's see if we can see where they go. Initially, you'd have to think about how that could be calculated and what kinds of values are needed to do it. For a sodium solid to be involved in this reaction, you have to figure out how you get it to something that you can measure. So you take sodium solid and turn it into a gas, and that's step number one. That's called heating a solid to a gas. That would be sublimation, actually. There's a certain amount of energy required for that. Physicists have figured it out. The second step is to take a chlorine molecule, half a chlorine molecule as a gas, and turn it into a chlorine gaseous atom. So half chlorine molecules and turn it into a chlorine atom. That can be measured. And then you have to take, the third step is to take a sodium atom, a gaseous atom, and remove an electron from it. Oh, that's ionization energy, right? Ionization energy of the gaseous sodium atom, and has an energy associated with it. People have calculated that. All those things require energy on this side. Require energy for now. The other steps of this process that you have to put together to figure all this out, takes a minute, don't worry, is to look at the right side where the chlorine gaseous atom adds an electron. Remember, that's favorable. That's electron affinity. And it's favorable for a halogen to pick up an electron. So that is a energy loss, loses energy, losing energy, or releasing energy, same thing. Releases energy when you add an electron to a chlorine atom. In the gaseous state, adding an electron, that's what the, electron affinity is defined to be. That would be step number 4 of this chart. And step number 5 then is to combine the other portions. So the sodium ion from step 3 as a gas, combining with the chloride ion as a gas. If you could hypothetically do this, that would end up with what the product is the sodium chloride solid. And there's a value for that, and it's measured in kilojoules per mole. So the most favorable step of this, releasing energy, is the last step where you form the solid sodium chloride from gaseous sodium and chloride ions. Why on earth does people want to make all these calculations? Well, the sum of the energy changes for these 5 individual steps, 1 through 5 numbered here, equals the net energy change for the overall reaction of just doing what we started off to describe here, making sodium chloride from sodium solid and chlorine gas. And so there's a theoretical way to do this, and there's a name for this process, and has some interested value, but it's not that we're going to make you calculate one, so don't panic. It's there, but let's look at it just from a mathematical standpoint for a minute. So the first step was a sublimation step, where you get the sodium going into a gas. The second step was breaking apart 2 sodium, or chloride ions, to make chloride atoms, chlorine atoms. And step 3 was the ionization energy for sodium. And the 4th step was electron affinity. And the last step is something called lattice energy. Wait a minute, we haven't come to that yet. So that's why this topic in this discussion here was going to be immediately fused and run into the next chapter topic. So using all these together allows you to add up all of the values that are known, calculated from separate experiments, and come up with the overall energy change for this reaction? Well, in order for this to make any sense, we haven't covered all of these things like bond dissociation energy. That'll be later, much later. Don't ask me for sure which chapter. We'll figure that out later. But what on earth is lattice energy? And that has to be part of what's involved in understanding how one would make this type of calculation. Thankfully, you don't have to. So what is lattice energy? Lattice energy has a funny symbol U. Seems kind of odd that there's a letter U here for that one. And it is the energy that has to be added to break up an ionic solid into individual gaseous ions. That's the way they're defined, is in terms of gaseous ions. And so you have to think in terms of ionic solids with pairs of cations and anions. And so various combinations of cations and anions are represented in this table. What kinds of possibilities do you see? Well, lithium could be with fluoride, chloride, bromide, iodide, and oxide, all of those possibilities. And each of them have different lattice energies. Or fluoride could be with lithium, sodium, potassium, beryllium, magnesium, calcium, and aluminum. Could be with any of those. And so each of those has an energy that has to be added to break up an ionic solid into individual gaseous ions. So you just pick one off the top and one down the side, and there's a value for you. Well, what is there to be known or noticed about these patterns? Well, some numbers are a lot bigger than others. And there's some generalizations that can be helpful to us when you stare at these just a little bit and recognize what in the world and how in the world the patterns evolve. Well, if you're looking in a simplistic sense, this is really actually fair, is to look at this set of values. All of those values, the energy required to break apart an ionic solid for those particular combinations, lithium, sodium, and potassium, with fluoride, chloride, bromide, and iodide, those are all values that are 1,000 or less. Well, the smallest one over here is for iodine. The largest one is with fluoride. Then, beyond that, there's some other values that are quite a bit larger, and those would be things that follow below, and from beryllium, magnesium, and calcium combined with any of those halogen anions. Those are 2,000 to 3,000 in general sense. But so are the values up here for oxide ions with the group 1 elements. Those are all kind of the 2,000 to 3,000 range. The highest one there, turns out in these two sets, is the highest one over here is with oxide. The highest one here is with beryllium. The lowest one is, yeah, let's make that comment here. The lowest one is in this section of the chart, and the highest one is here. There's some patterns going on here. Let's see what makes sense of that. And yet there is a third set in here that's even higher than that 3,000 value, and those would be the oxide ions with group 2 elements, or aluminum with any of those halogens. What on earth explains these patterns? The highest one this time is aluminum with oxide. Wow, that's really big compared to some of the other numbers. Nobody wants to memorize them. It's okay. Don't even hope to memorize them. I certainly don't either. So the lattice energy, remember the definition here, is the energy required to completely separate a mole of a solid ionic compound into gaseous ions. That's how they use these definitions. And the direct calculation is using something called Coulomb's law. That's from physics. No, you don't have to know that one particularly, but let's think it out and see what it's related to. It's related to the potential energy between two ions, stating that it's directly proportional to the product of their charges. So the charges of those ions are going to be important. And it's also going to be directly proportional to 1 and inversely proportional to the distance, the separation between them, with K being a constant. Well, here's the equation. The lattice energy U is a constant times the product of the charges, so Q1 and Q plus and Q minus are the charges of the cation and the anion, and R therefore must be the distance between the ions. So it's inversely proportional to the distance. Distance would be R, and the charges are Q plus and Q minus. So the product of those divided by the distance gives us a way of making sense of a lattice energy. What does that mean? Keep thinking. So if it's related to these things by that thing we has a law called Coulomb's law, what is the result? The lattice energy is going to increase as the charge increases. So the bigger the value of Q, the bigger the value of the lattice energy. So U goes up when Q goes up, and or when the radius between the ions, or the distance between the ions decreases. So when R decreases. If that value goes smaller, the whole overall value of the lattice energy will be greater. Does that make sense mathematically? So here's a few compounds and their corresponding lattice energies. Apologies for the overlapping letters here. Let me see if I can fix that. Okay, that's better. So let's look at some compounds and some lattice energies and see how this relationship with charges and distances are going to correlate to this relationship shown in the equation. You don't have to calculate one, but let's see if we can make sense. So magnesium with fluoride, magnesium and oxide, we have a +2 cation and a -1 cation, or anion, +2, -1, or a +2 and a -2. Well, guess which one is going to have a larger lattice energy? Take a look. The magnesium oxide, because with the increased charges, their value on the top of that equation becomes larger. The sizes of the ions do make a difference, but oxide and fluoride, at least they're adjacent to one another in the second period, and so similar sizes of ions, not exactly the same, but not a huge difference. Let's try some other comparisons. Oh yeah, so there's the charges +2 and -1, +2, -2. This one comes out to be, the second one comes out to be a larger lattice energy. Nope, we're not calculating the numbers, but those are the numbers provided for you. Okay, so another comparison. Lithium with fluoride and lithium with chloride. Oh, so comparing those two, the charges are both single plus and single minus in each case. But what about the lattice energies and how does that fit? So the charges are all the same. It's not going to be a difference in the charges, but it's going to have to do with the distance between the ions. And so which ion is bigger? The fluoride ion or the chloride ion? Think closely, look back at your periodic table. The chloride ion is going to have a third shell that's full, and the fluoride ion has a second shell that's full. So the second shell full is smaller than the third shell full. So the smaller radius means a greater lattice energy. There you go. So the lattice energy is larger for lithium fluoride than for lithium chloride. Because this radius, the distance between the ions, think of R like radius, but that's not exactly how it's defined, for fluoride ion is smaller than that for chloride ion. All right, so think about these crystalline structures. These are simplified diagrams for cations and anions in a crystalline structure. And remember that the lattice energy, the energy that it takes to break apart one of these things, is going to increase when the charge goes up or when the distance between things decreases. So the sizes of ions make a difference, and their charges. Here's another interesting aspect of this conversation. And if you look at these lattice energies, what else does it relate to? And I think this is where we have some relevance to these values instead of just a mathematical or numerical exercise. The lattice energies are relating to how hard it is to take apart an ionic solid. So that has to have something to do with how they melt. And so if you have a larger lattice energy, that means they're more stable and it takes more energy to melt them. So the melting points should be higher when the lattice energy is higher. So which ones have the highest lattice energies? The ones that have doubly positive cations or anions or both, and they're higher when you've got doubly charged species, and the melting points are going to be somewhat higher, more energy to melt them. And so this varies a little bit, but the lattice energy for lithium fluoride is higher than lithium chloride, so its melting point is higher of those two. Again, comparing lithium chloride to lithium bromide and lithium iodide. So these are decreasing as you go down, and so are their melting points for that set of compounds with lithium and halogens. I shouldn't have jumped to the bottom of the chart so fast. Let's look in the middle first. So sodium chloride or sodium with various halogens. Sodium fluoride is not listed here. And as you have increasingly larger ions, the lattice energy goes down, but the melting points also go down as the lattice energy goes down. Potassium with various halogen anions. the lattice energy goes down as the radius of the anion gets bigger, and so does the melting point. Interesting how you can see some patterns there. Now, let's go back to these other ones here. The doubly charged ionic species, magnesium's +2, right? And chloride -1, oxides -2, oxide -2, and magnesium +2. So you've got some very large lattice energies for those compounds. Turns out that they sometimes actually decompose or sublime instead of actually melting, because their melting points are rather high at times. So the last ones are not as easily generalized, but the melting points correlate to the lattice energies in a reasonable fashion for those first groups with group 1 elements and halogens. Interesting. Okay, so let's apply this to some examples. If you have 2 alkali metal halides, so that means you've got something from group 1, right? Group 1A with a group 7A anion. One of them is going to have a larger lattice energy, and which one is going to be the smaller lattice energy? Think about that for a minute. So there's 2 different ones here. Each of these examples represents a pair of ions, 1 plus, single plus, cation, single minus anion. And which one's going to have the larger lattice energy? So the lattice energy increases as the charge increases, but there's no difference in charges here. They're all +1, -1. But the lattice energy will be increased with the smaller radius. So the smaller lattice energy is going to be with a larger radius, or larger distance between ions. I keep trying to say radius because it's R. And the larger lattice energy will be the ones that are smaller distance between ions. So the larger lattice energy is this compound. The smaller lattice energy is the larger ions. It correlates to what we saw on the previous page. So let's look back at that. As the ion gets bigger that's combined with lithium here, the anion, the lattice energy goes down with each successively larger halogen anion. That fits. Okay, we'll try another one. And let's see what we can do with these ones. These are colorful diagrams. And on the left, we have green and purple spheres. On the right, red and blue. And one of them is sodium chloride and one is magnesium oxide. Given that as a piece of information, the sizes of the ions are not necessarily going to help you. If you define this to be those 2 compounds, you can determine which one's going to have the larger lattice energy and which one is which, assuming they're drawn to some kind of scale. So in each case, you have to think about what ion is going to be larger and smaller, which in a general sense are larger or smaller ions. So larger ions are which, and smaller ions are which. Whoops, I didn't spell that carefully. Smaller ions. So thinking about the periodic table and how ionic radii work, on which side of the periodic table are they larger and smaller? Smaller ones are what happens when you lose electrons from a metal and lose an outer shell and contract down to the next smaller full shell, like a noble gas configuration. The larger ions are the ones that get fuller shells when you have nonmetals adding electrons. So that tells us that the small spheres have to be the cations, the metals. And so those are metals, and which one is going to be bigger than the other? Oh, well, that's the next question. So sodium and magnesium side by side on the periodic table. If sodium has lost 1 electron and magnesium has lost 2 electrons because it's +2 and +1, which one of those 2 is larger? So sodium ion compared to magnesium ion, which is bigger? The one which has the greatest number of protons in the nucleus pulls on 10 electrons differently than the one that has fewer protons pulling on 10 electrons. So this one is going to be smaller. So that would be the magnesium cations on the right. Similarly, we can also make some generalizations from what we know about chloride and oxygen. So chloride ions are full octet of the third shell full in their chloride ions. And so that's going to be different than oxide ions, where you have a second shell filled, and that would tell you which one is larger. So the oxide ion compared to the chloride ion, the larger one is chloride. So chloride better be this one, and sodium with it. And oops, put charges on those, that makes more sense. And if this is the magnesium cation here, the corresponding other ion here would be the oxide ion. Does that make sense? So there's your answers to that one, revealed nicely on the bottom. All right, one more example with ionic solids and trying to make sense of their lattice energies. So if we're given a set of compounds and we're going to decide what their energies are, greatest to least, which one has the highest, which one has the smallest, what were the factors that go into it? So lattice energy was that funny value U, is increases when the charge is increased or when the distance between them is smaller. Okay, so the largest one would be things that have +2 charges or small distances, small ionic radius. So let's just write ionic radius instead. That's what we're thinking about, ionic radius. All right, so on these 4 choices, the ones that are going to have the largest lattice energies have to have larger charges. Well, most of these things look like singles except for magnesium. So that's a +2 ion, and therefore it's going to give it a larger lattice energy. Okay, that puts it on the larger side. And then comparing chloride to bromide, oh, which one is bigger? Chloride versus bromide ion, which one is going to have the smaller ionic radius? Well, chloride is in the 3rd period, and bromide is in the 4th period. Well, I'll write it here. And so that tells you that the one with more shells is going to be larger, so chloride is smaller than bromide. So the smaller ionic radius gives us a larger lattice energy. So this makes 2 reasons. It's got a smaller ion, the chloride ion, and anything with bromide is going to be a lesser, so that's going to be a lower lattice energy, given a choice between these two. So lesser lattice energy for potassium and bromide compared to this one, than KCl. Now, if you compare potassium chloride and lithium chloride, oh, what do you have to think about those two? So we have to compare those two. Lithium ions versus potassium ions, get the right thing here. Potassium ions. When you have a lithium ion, its configuration is effectively the same as helium. That's just the first shell full. And a potassium ion is effectively the same as argon. Oh, well, then which one's smaller? Well, this lithium ion is certainly much smaller than the potassium ion. So the potassium compound is going to have a greater lattice energy, that's the letter U, I guess, than lithium chloride. So where was the greatest one? This one's going to be large because it's got the +2 cation. And the one that's going to be this, I said that backwards, the larger, greater, sorry, backwards. The potassium has a larger radius, and so that means has a lesser value of the lattice energy than lithium. So potassium will be less than lithium. The lesser lattice energy goes for potassium compared to, sorry, KBr versus KCl. And then the largest one would be the one that has a +2 ion. Wow, that takes a minute to think about it. So this one's the largest, the magnesium chloride. The lithium chloride would be second, potassium chloride less, and potassium bromide last. Wow, that takes some thinking, but at least it makes a way of making use of those kinds of comparisons. I hope you find that helpful. Please ask more questions as needed till you get these topics figured out. They'll be on our next exam, of course.